And I guess the previous session would have actually woken you up anyway. So I'm going to talk about the emerging landscape of data and how we are seeing a transformation in the way we are using different data technologies today. And few of the things that I will cover is essentially the traditional databases, and then go on and talk a little bit about NoSQL stores, and then move on to a product called vFabric, which actually somewhere sits in between a NoSQL and a relational data store. Is there anyone in the room who's a developer and has never used relational databases? Not a single hand. Everyone has used relational databases, right? It's been around for, what, 40 odd years now. Very, very rich query language. Everybody has used, inner joins, referential integrity. Very strong focus on consistency model as well, right? It guarantees the data that you're going to put into the database is going to be consistent and durable. And there are a lot of frameworks that have evolved over a period of time, which make the life of us developers very easy when we work with relational databases. Hibernate, right? JPA, Spring JDBC. So there's a whole body of industry knowledge about how to use relational databases, and almost every application today uses relational databases, right? But there are some challenges as well. How many of you have heard of the CAP theorem? I see a few hands. Okay, so there was a paper that was published which talks about the three competing aspects of persistence in a distributed environment. One is consistency, second is availability, and the third is partition tolerance. What does it mean? It means that a system that you build which is going to store data and it's going to distributedly store data in multiple different nodes will have to make compromises in at least one of these axes. You can't really be always consistent, always available, and always persistent. Always partition tolerant. Now, relational databases actually choose consistency at the cost of availability. And there's typically, no multiple relational data stores, so you can't really horizontally scale it out. So there's no question of, partition tolerance being a problem. But availability is a problem, right? So when one thread comes in and does a write, the other thread, depending on the isolation levels, will ideally actually have to wait, and your system is no longer available for that duration. The other big challenge because of this is the fact that the relational databases cannot really scale out horizontally. I can't put multiple different, relational databases boxes in a cluster and make it scale. It also has this strong assumption that asset semantics are important, right? Transaction management important, consistency is important. But we are the Facebook generation. I think in a system like that, consistency is not perhaps that paramount. So for example, if you post a message on my wall, it's not necessary for me to see that message right away, right? It can be an eventually consistent system wherein the message can, come into my wall maybe a few minutes or maybe a few hours later. Really doesn't cost anything. And the other challenge that we have with relational databases, because of transactions, it depends on disk IOs, which makes it slow. Disks are physical devices, they have to move. And certain use cases have suboptimal performance. Now, a typical scenario that we see today in any web-based application is the fact that you have peaks and lows in terms of utilization. A lot of users come in during specific time and then it goes down. Now, when we scale, when we want to address this diverse need in terms of scalability, we can actually cluster our application tier and add more and more nodes to address the peak nodes at the high times, right? We can't do that with a relational database. The database remains just one. So that ends up becoming your single point of failure, your single point of bottleneck. And then when load goes down, you should be able to dynamically scale it down as well, right? Again, you can't do that with relational databases. So to address some of these challenges, NoSQL databases have emerged, and they have some similarities. There's lots of them. I'll just briefly touch upon them. They address high performance. So they take away the IO penalties that a disk-driven relational database puts, and they perform very quickly. They have scalability, right? You can put them in a clustered mode. Many different nodes running together, coordinating your requests to make the system scale. And they also offer what is called a rich data model. So when you use a relational database, your table defines what data you store in it, right? So you say certain columns, and all the data that goes into the table has to adhere to those column definitions. That doesn't hold good for some of the NoSQL data stores because they're schemaless. Every row that you send in a NoSQL store could have n number of columns, different number of columns. But then every system, every technology has trade-offs. The trade-off here is they offer limited transactions. So your consistency model is compromised. And there are way too many of them, right? You have graph databases. Neo4j is a classic example. So how many of you have LinkedIn accounts? Almost everyone, right? So when you go to a LinkedIn account and open anyone's profile, it shows you on the right-hand side what is the shortest path to that guy, right? So your connections, and then maybe his connections, and then to that guy, right? Just imagine doing this kind of a computational logic in a relational database. If you were to write this query, it's very, very difficult. You can't really do this on the fly. So there are specific databases, graph databases like Neo4j, which address that need, specialized use case. We have key value stores, which are very simplistic in nature in terms of data storage. It's almost like a distributed hash table, right? A hash map that you have in Java. You have document databases, which allow you to store data in the form of a JSON data model or an XML data model, and then you can query to get the data out of it very easily. MongoDB, CouchDB, very good examples. And then you have columnar databases, which are driven on top of Bigtable, paper by Google, which is, again, almost like an inversion of the row-based relational model. But what is similar across all of them is they scale. They allow you to run it in a distributed mode. However, because there are so many of them and they address different needs, each one of them comes with a different API. So if you were to talk to a graph database or a key value database, their APIs are different. There's no similar API that you see in SQL. And SQL, like if you use SQL, DB2, Postgres, Oracle, MySQL, doesn't matter. SQL is SQL everywhere. So there's no one unified API access for all of the systems. Now, though I say that relational databases are being challenged by the NoSQL stores, the fact remains that if you look at the lower graph, you see the emergence of the NoSQL stores. They are growing very, very quickly. But when you compare that with relational stores, you just see a blip, a very, very small blip in the right. So it's not something which is going to replace relational data stores very, very soon. Right? It will perhaps be happening over a long period of time. So don't throw away your existing knowledge that you have on RDBMS. Now, so when we looked at these two technologies, right, NoSQL and SQL, we can see that there are some contrasting trends. One of them is absolutely consistent, not so scalable, right? And there's a unified API language, irrespective of which relational data store you choose in case of relational database. In case of NoSQL, there's no single API. Scalability is guaranteed, performance is guaranteed, transaction semantics are questionable, right? So what if we could have a solution to both of these scenarios, right? What if we could have a product which would actually address both of these needs at the same time? If you could keep your existing knowledge of SQL and extend that in a manner that you could scale your system, support transactions, how wonderful would it be? If you have an existing application which is working on a relational database but it's not scaling because there are way too many users, more than you ever expected, how nice would it be for you to be able to port that application seamlessly without changing your data access code? So that's where SQLFire comes in. So what is it? It's a memory-oriented relational database. It's a distributed database, but it's memory-oriented. And because it is distributed, obviously it uses resources from all the nodes that is deployed on. The disk, the memory, the CPU, everything gets pooled together as a single whole unit. It supports ACID, so it has transactional concepts, just like relational databases do. And it supports JDBC, it supports ADO.NET. So if you have a Hibernate application, it'll just work. Plus, it has SQL conformance based on the ANSI SQL 92 standards. So how does it scale? Very simple. Just like you scale your application tier, you keep adding more and more nodes whenever you need, and then you can dynamically bring them down. And it's just a single command line for you to execute the addition of a node to the cluster. It's very simple. It just listens on a port and connects to the cluster and redistributes the data and the load. So how does it do it, right? It sounds like a lot of magic. Actually, it's very simple. It doesn't really change any of the data manipulation language features that you have, like an insert, select, right? None of those change. But it adds some additions on top of your DDLs. So when you say a create table, for example, you could go and say create table blah blah blah, and then in the end say partition by primary key. I'm just making one example. There are other ways to partition it as well. So when you say partition by primary key, the system intelligently understands how it is going to break the data out into multiple different nodes. And the beauty of it is, you as an application developer, when you write a client, you don't need to know which node has what data. You just go and query it like you would query any relational database. The system will automatically guarantee that there will be a single hop. Your query will go and hit the node where the data resides. So if I fire a query which says, get me a customer who has placed an order greater than 10,000 and whose customer ID is this, it'll go to the node where that customer ID resides. So it's a very, very simple mechanism of sharding out your data without being invasive. There's another concept which is called replication. What it essentially does is it copies over the data into every node that you have. So that's another scalability component. For example, if you are an e-commerce store and you are selling products, every customer who comes to your site is going to read the products, right? That's going to be your maximum hits. Everybody is going to try and read some product description, some product pricing. And in this scenario, if you could replicate, if you could copy over the product data into all the nodes, in that scenario, your clients could read the data from any of the nodes, right? So you have automated the mechanism of scaling the read requests. So that's replication for you. When a write comes in though, SQLFire decides whichever node it goes to, that's the primary node, and that's where the write will occur, and then it will synchronize with the other nodes dynamically. And I'll talk about how it does it, still guaranteeing the performance in a distributed environment, because that's one of the challenges that you have in a scenario like this. Plus, is also addresses one, can I take the questions after the? Yeah, so one of the interesting things that it also does is it supports multi-site WAN gateway. So if you want, so you have high availability, right? Now you have partitioned data. So let's say I've partitioned your customers based on customer ID, and I have a concept called redundancy. I could go and say the customer ID is partitioned, but it will have a redundancy level of 2. What it means is it's going to copy the same customer's data into 2 different nodes. So even if one node goes down, the second node can still service your request, and you can choose a different number of redundancy depending on what your availability requirements are. So that's availability within a single data center. What if the entire data center goes down? Right? What do you do? So we have a capability called async WAN gateway, where the data can get replicated across to another data center asynchronously over the batch mode, and it's very, very performant. So that's a mechanism for you to provide for disaster recovery. Coming back to the concept of partitioning replications, we also have another concept called collocation. So in the same example, if we look at typical web e-commerce site, you have products, you have customers, and then you have something like orders. Now orders, interestingly, are always related to a customer. I will never look up an order of customer A and customer B is going to make that request. That will never happen. So I can co-locate that data. I can go and say, keep all the order data for customer A with the customer, so that in a single request I can pick it up. Right? So you can partition, you can replicate, and you can co-locate. So what are the trade-offs, right? It's all about trade-offs. The trade-offs here are fairly interesting. We believe we have actually, with this product, improved upon the transaction management models that you see in typical distributed systems. So we don't do XA. So in a typical distributed relational database, you would be doing a 2-phase commit, which is expensive. Here what happens is each member manages its own transaction state. And then there's a coordinator sitting somewhere else which says, okay, I've got the acknowledgement, now it's written to the final store. Now, though it is memory based, it has a persistent store. You could optionally ask it to put the data into the disk for recovery, which means that if a node goes down and comes back up, it can read everything from the disk and reinstate the state that it was in. One of the interesting things that we have done from a transactional management standpoint is we have standardized on a read committed transaction level. Now this is a problem, for example, if you're using a cache mechanism, one of the things that you're always challenged with is the fact that the data is in the cache, but it hasn't hit the relational database, and if I'm reading it from the cache, I might actually get a non-committed, uncommitted read, right? So in SQLFire, every read is guaranteed to be reading only committed data. So it does an in-place copy of that data in a different row and keeps it there till the time all the coordinating nodes come back and say, it's committed. And because all of these writes are actually happening in memory, it's really fast. It really doesn't need to go to the disk and spit it out. We also support XA transactions, but that's not for internal usage. SQLFire internally doesn't use XA. But if you want to tie in SQLFire with another system which supports XA, SQLFire can participate in it. So if you have a relational database or a JMS or a different messaging system where you want the data to also go for other systems to pick it up, you could do that as well. How many of you have used NoSQL stores? Very few hands. MapReduce? Yeah, I see a few of them. So the whole concept that we do with a system like this is the fact that instead of taking the data to the behavior, we take the behavior to the data. So most of the times when we are writing Java applications and we want to apply some logic, the first thing that we do is we go and query the database to get the relevant data, then apply some logic, and then get the result out to back to the client, right? That's expensive. Why should I take the data and make that entire network traffic? With a distributed data grid, what you could do is you could put the logic right inside the grid, right? Embed the logic right inside the grid, and then fire that logic in the grid in a distributed manner, and then the coordinator could pick the result and give it back. So that's almost like a MapReduce, right? So we support a different paradigm of MapReduce using embedded SQL procedures, procedures, and these are written in Java. So these are Java procedures, and you don't need a server restart or anything. If there's a procedure available for you, you invoke that procedure with your jar file. It will go and deploy it across all the nodes, and now you have the ability to run logic within your data grid to actually address the need of your programming logic. So in summary, what SQLFire does is it provides you high speed. You don't need to throw away your existing investment in the SQL language. If you are using a third-party framework on top like Hibernate, that gets ported. At the same time, it gives you the benefits of a NoSQL store like scalability and performance. So that's about all I had. If there are any questions, I could take those. Yes. So it's not really applications. We have commercial customers who are actually using this. Some of them are BFSI segment where obviously the data is pretty, data and transaction consistency are very important. I can't name the customer. We can. Any other questions? Yes, we have a very solid console which gives you performance statistics as to how many hits are going, right? What is the network lags that you are seeing? So there is a very detailed console. Thank you.